Welcome class, myself Professor D.S. Rai, Professor Department of Civil Engineering, BVD, ITM, Lucknow. We will cover today KCE 076 Urban Transportation Planning. Today lecture is lecture 24, in which we will cover tip assignment. A references that I have taken Chakravarti Partho and Adas Animes, Principle of Transportation Engineering, Papacosta CS and Verivideras PD, Transportation Engineering and Planning, Kadiali and Lal, Principle and Practices of Highway Engineering, Naptel, and some material have been taken from internet. The contents today will cover traffic assignment, aggregate network, diurnal daytime, pattern of demand, defining the network, a spanning tree, KRUSKAL'S algorithm, Prim algorithm, Dijkstra algorithm, Floyd algorithm, divergent curve, traffic assignment model, equilibrium assignment, all or nothing assignment, capacity restraint assignment, logit or route choice model, dial or torch algorithm, dynamic traffic assignment model DTA. Today we will discuss traffic assignment. We have already covered traffic generation, traffic trip distribution, mode choice, and last, after finalization of everything, then we have to choose a route, by which route trip could be made. So, the traffic assignment is the process of allocating set of trip interchange to the specified transport system or routes. It requires a complete description of proposed or existing transportation system and origin and destination matrix of interzonal trip movement. The major aim of traffic assignment procedures are to first estimate the traffic volume on the link of the network and the turning moment at intersection. Furnish estimate of travel cost between the trip origins and destination for use in traffic distribution. Now, aggregate network. Obtain aggregate network measure, that is a total vehicular flow, total distance covered by the vehicles, total system travel time. This has to be known. Next, estimate zone to zone travel cost for a given level of demand. Obtain reasonable link flow and to identify heavily congested link. Estimate the route used between origin and destination pair. Analyze which origin and destination pair that uses a particular link. Obtain turning moment for a future junction. Primary aspect of traffic assignment. Three primary aspects must be kept in mind before carrying out traffic assignment questions. Number 1, interzonal personal trip or interzonal vehicle trip. Diurnal distribution of demand. direction of travel. Now, person trips and vehicle trips. Person trip provide an indication of the passenger through put that desire to use a particular route. However, the level of services that a trip maker experiences traveling on a route is related to the vehicular flow. Interzonal personal trip must therefore be translated into vehicular trip prior to performing the assignment. Mass transit system. Whether the proposed fleet size, schedules and frequency provide sufficient capacity to meet the anticipated interzonal personal trip demand. Diurnal day-to-day pattern of demand. The demand for transportation exhibit a highly peaked pattern with a sharp peak period in the morning and evening. It is appropriate to investigate the performance of the transportation system under peak demand conditions when capacity limitation become most critical. The time variation of the demand is most relevant to mass transit planning, because the scheduling of service is typically tailored to the variation of demand over the hour period. Now, come to the trip direction. Predominant direction of the travel during the morning peak period is towards major activity center like CBD, schools, college, etc., etc. And the reverse is true during the evening peak period. Directionality factors by time of day and trip purpose are typically used to convert production and attraction PA matrix to origin and destination OD matrix. Link cost function. As the flow reaches towards the capacity of the stream, the average speed reduces from the free flow speed to the speed corresponding to the maximum flow. The minimum path computed prior to the trip assignment may not be minimum after the trip are assigned. Now, a number of iterative procedures are available for necessary convergence in this regard. The next is link cost function. The relationship between the link flow and link impedance is called link cost function. An example of link cost function: T is equal to T 0 into 1 plus alpha x by k to the power beta, where T and x is the travel time and flow respectively on the link. T 0 is free flow travel time, k is the capacity of a link, alpha and beta are the model parameters. For the typical value, alpha is equal to 0.15 and beta is equal to 4.0. Now, defining the network. Urban road network includes intersection streets in an urban area through which traffic moves. These elements can be translated naturally into a structure of nodes and links respectively. Transit networks represented by a simple linear network in which transit station like bus station are represented by nodes and line haul portion of the link. Destination node transit line, origin node loading link, unloading lane. Fixed facilities are specified by a set of nodes, that is intersection and interchanges and the link, the major arterial, expressway or freeway. The interzonal flow refers to the demand for travel between the pair of zones. The link flow is the flow that occurs on the specific link I j, I means origin zones and j is destination zone of the transportation network and is the sum of all interzonal flows that happen to include that particular link on their preferred path. Each network link is typically associated with some impedance that affect the flow using it. The impedance can represent distance, time, cost, utility, etc. When flow involves people, the term level of services is usually instead of impedance. Level of services is a very important parameter for functional evaluation of the network. Centroid, source and sink. The transportation planning process for the urban area is the typically based on the portion of the area into the traffic zones. Each traffic zones is represented by nodes known as centroid. The network representation of the urban area will include many other nodes representing intersection, bus stop and other transportation facilities. The centroid, however, are those source and sink from the points the tip originates, that is the source, and where the ends like a terminals, then it is called sink. Nodes where the traffic originates and to which traffic is destined. Once the set of centroid is defined, the desired movement over the urban network can be expressed in terms of origin destination matrix. The nodes in the middle of the zone is the centroid. It is connected to the road network by a special centroid connector links known as connectors. So, now come to the spanning tree. It is useful to understand the some network properties. First, minimum spanning tree and second, shortest. So, stage first, it can be seen here that blue lines are all weather roads and yellow lines are all others road. In second stage we can see this is the links development of this is the development. First of all this has been taken, after it was found that this should be also connected with the all weather roads, and this should be also connected with here, and some extension of the roads are also taken up. Then the next development are complete network is covered with the blue lines, means all weather roads, that is the stage 3. So, the development of road networks are continuous process. Now, come to the spanning tree. Minimum spanning tree. A spanning tree, a tree with the required number of link to ensure connectivity of the network, that is n minus 1 link to connect n nodes. Link will be always less than 1 of the nodes. Minimum spanning trees, a spanning tree with a minimum total cost or length. In many systems such as highway, computer networks, telephone line, television cables, etc., it is necessary to identify a minimum spanning tree. Two important features of a minimum spanning tree. Number 1, possible multiplicity. There may be a several minimum spanning tree. For example, if all weights are same, every spanning tree is minimum. Number 2, uniqueness. If each edge has a distinct weight, then there will be only one unique minimum spanning tree. We can see here, this is the spanning tree. Here we can see that each nodes, these are the nodes. These are the nodes and these are the link. So, there are A, B, C, D, E and F, 6 nodes. There are 6 nodes and a spanning tree should be less than 6, n minus 1. So, what happened? You see here, A to B have 2 weightage, A to C 4 weightage, B to D 4 weightage, D to F 1 weightage and E to F 1 weightage. So, our spanning tree are A, C, A, B, D, E and F and E. So, this is the spanning tree, which we have 5 links and 6 nodes. Though there are many links, there are 7 links are available here, but the spanning tree will have only 5 links. So, now come to the different algorithm. There is a greedy algorithm. Take a graph with n vertices, vertices means same nodes. Keep adding the shortest least cost edge, while avoiding the creation of cycle until n minus 1 is have been added. So, this is the algorithm. There should be no cycle until n minus 1 is have been added. So, come to the. So, this is a network, a same network A, B, C, D, E, F, 6 nodes, and there are 7 numbers of links. Is it? So, now come to the starting from last, this is the F node, and starting with the minimum cost function, say this is the 1. So, we have this is the spanning tree F D, this is the 1. The next higher is 2. So, we can connect after that, means after connecting F and D, then we go for next 2. So, F E will be taken up, and we can see here the A and B has a same weightage of 2. So, this will be also taken up here. So, A and B has also taken up. So, in a spanning tree we have now up till now, that is E F, F D and A B. How many nodes we have? We have 6 nodes. So, our spanning tree should be 5 links. So, now come to the next one. So, after 2, the weightage of a link is 3. So, B and C will be the part of a spanning tree. So, we can see here this is the, now the spanning tree will be A, B, B, E and D, F. So, we have 1, 2, 3. Now, the next is, next weightage is 4 here. So, A and C will the link of the spanning tree. So, now we have A C, A B, B E, E F and E D. So, how many links we have now? We have 1, 2, 3, 4, 5. How many nodes we have? 6. And how many links we have now in a spanning tree? 5. So, with the 5 we have connected all the nodes of the network, and so the minimum cost of a spanning tree will be by weight, that is 1, then 2, this is 2, again 2, here this is 2, then the 3, this is 3, and this is the 4, 4. So, the minimum cost of a spanning tree is 12. This is the KRUSKAL'S algorithm. Now, come to the Prim's algorithm. Start at any vertex in a graph, vertex A for example, and find the least cost vertex, vertex B for the example, connected to the start vertex. This is the first algorithm of Prim's. Now, from either A or B, find the next least costly vertex connection without creating a cycle. Cycle is completely provided. So, vertex C for the example. Now, from either A, B, C, find the next least costly vertex connection without creating a cycle, and so on. Eventually, all the vertices will be connected without any cycle, and an MST will be result. So, now come to the prime algorithm. See here, this is a problem, find the minimum spanning tree for a given network. Solution, step 1, what we have to start from a starting point A, the minimum costly connection is taken. So, here is a 2. So, first of all 2 has been taken. This is the original network. Now, there is no, now come to the point B, node B. Node B has, apart from 2, there are 2 link having weight 3 and 5. So, we will take 3, a minimum of these 2. So, B and E has been taken. Now, come to the node E. Here again we will choose a least costly link. So, what we have, there are 6, 7 and 2. So, least costly is 2. So, we will take 2. And now we have reached at F. Here again the least costly link is 1, there is only one remaining. So, now we have A, B, B, E, E, F and F, E, F. Still there are only 1, 2, 3, 4 links. So, now we come to here again at A, where the next costly links is here at A. So, here will be the 4. So, what we have, a minimum spanning cost will be AC, CB, AC, AB, BC, not BC, AB, BE, EF and FD. So, our spanning tree will be, a minimum cost of a spanning tree will be 2 plus 3 plus 2 plus 1 plus 4. 2 plus 3 plus 2 plus 1 plus 4. So, we have a spanning tree, minimum cost of a spanning tree is 12. So, thank you very much. We are closing here, we will take up in next class.